Okay, today we're looking at section 7.6, which is exponential functions. Hopefully by the end of this section, you can say that I can evaluate and graph exponential functions. So what are we going to be doing exactly? Well, one of the things we might have to do is determine whether a table represents a linear or an exponential function. So we should have seen earlier that if we got a linear function, that it's increasing by the same amount each time. For an exponential function, what we're going to look at is the ratio of the y values. So first of all, if I looked here and I said, okay, I know I'm increasing by 2. From here to here, I'm increasing by 4. So I know that it's not linear because we're not increasing by the same amount each time. So then if we want to check to see if it's exponential, what we do, we take consecutive y values and we divide them. So we take 4 divided by 2, and that would be a 2. And then I would take an 8 divided by 4, and that would be a 2. And then I take 16 divided by an 8, and that's 2. And I take 32 divided by 16, and that's 2. And then 64 divided by 32, we know that that is 2. So that we say that there is a constant ratio between the y values. So we would say that this one here is exponential. Okay, if we look at the second one, and we look here, first we check to see if there's a common difference. We went up by 3, 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 we went up by 3. So we would say that there is a common difference of 3, so this one here would be linear. Okay, and if we had to explain it, again, the first one we could say that there's a common ratio or a constant ratio. On the second one, there's a constant difference. Okay, easy enough. So now we might have to look at an equation and tell whether it is a exponential or a linear. So if we look at this first one, this one would be exponential because it follows this pattern right here where we have y is equal to a times b to the x power. We have something, a base to an exponent of x. Okay, so this one is exponential. If I look at the second one is an exponential again. Okay, if I look at the number 5, now we're back to a linear pattern. Remember, linear was something that was in this form typically, y equals mx plus b. So this one would be a linear. Okay, and this one here again would be an exponential. So hopefully we can look at an equation now and determine whether it's going to be a linear or an exponential. Okay, next thing we're going to have to do, we're going to have to be able to evaluate a exponential function. So if you have a calculator, these are quite simple. So I simply plug in the value, and then I simply use a calculator, and I take 4 to the third power, and I would get a 64. So y would be equal to 64. On the second one, if it's in function notation, so now I'm going to put in a 5 wherever I see the x. So the function value at 5 is equal to 2 times 3 to the 5th power. So what do we do first? We do 3 to the 5th power, and that's 243. So I really have 2 times 243. So the function value at 5 is really 486. Okay, this next one, we got a function value at, or h of t is my function. So now I'd have a function value at 8 is equal to 60 times 1.07 to the 8th power. So I take 1.07 to the 8th power, and the answer there is quite large. So then I'm just going to use my calculator, and from that I'm just going to times by 60, and I get the function value at 8. I'm going to say is approximately 103.09. Okay, for this next one, I got y is equal to 5 times 7 to the x power, so it's 5 times 7 to the 0 power. And we should know by now that 7 to the 0 power is going to be a 1, so it's 5 times a 1, so y is equal to a 5. Okay, so hopefully we can say that we can evaluate, with use of a calculator, exponential functions. And then what we finish with is just how do we graph an exponential function. And to graph an exponential function, we're going to do the same thing that we have been doing, and that is just making a t-chart, plugging in -2, -1, 0, 1, and 2, and just finding the values. So if I plug in a -2, that would be 2 to the negative 2 power, which ends up being 1 over a 4. If I put in a negative 1, it would be 2 to the negative 1 power, which ends up being 1 over 2. 2 to the 0 power is 1, 2 to the first power is 2, 2 to the second power is 4. And then I can just come over to my graph and graph those. So I got a negative 2, 1/4. I've got a negative 2, 1/2. I've got a 0, a 1, a 1, 2, a 2, 4. So what I end up with is this curve that looks like so. Okay, so let's try a couple more of those. So if I were to look at this one, 3 times 2 to the x power. Okay, so again, we got an x, we got a y. So I've got a negative 2, a 0. Oh no, not a 0. Negative 2, a negative 1, a 0, a 1, a 2. If I put in a negative 2, I'd have 3 times 2 to the negative 2 power. So that's 3 times the 4th, which is 3/4. If I took 3 times 2 to the negative 1 power, that would be 1.5. If I took 3 times 2 to the 0 power, that's going to be a 3. 3 times 2 to the first power is going to be a 6. And 3 times 2 to the second power is going to be a 12. So we should be able to get an idea of what's happening here. I got a 3/4, I got a 1.5, I've got a 3, I've got a 6, I've got a 12. So I've got this curve like so. Okay. And this one, ooh, doesn't look very good. I got a y equals 1/4 times 2 to the x power. So if I made my t-chart now, I've got a negative 2, a negative 1, a 0, a 1, a 2. If I put in a negative 2, it'd be 1/4 times 2 to the negative 2 power. So that's really 1/4 times 1/4, which is 1/16. I've got a 1/4 times a 2 to the negative 1 power, which is 1/8. And then I've got a 1/4 times 2 to the 0 power, which would be 1/4. And then I've got a 1/4 times 2 to the first power, which is going to be a 1/2. And then I've got a 1/4 times 2 to the second power, which is going to be a 1. So I've got a 1/16. I got a 1/8. I got a 1/4. I've got a 1/2. I've got a 1. This is one that grows very slowly. Okay, that is all I have for this section. So hopefully you can say that I can evaluate and graph exponential functions. That is a wrap.